So let us simplify what is UH. So UH as a function of x, we will rearrange the terms, and this would be g of n1 plus n2 plus n3 plus h times n1 plus n2 by 2. In fact, I will show this later, but you can check that summation of all NAs, A going from 1 to n plus 1 is 1 at all x. This is a property of the shape functions that we have defined, or the basis functions that we have defined. You can manually check it, but I will show you that this holds for all the general shape functions that we design. So this quantity then becomes 1, and UH of x, you can check, will turn out to be g plus h times 1 minus x. And this is the same as exact solution. For f equal to 0. Of course, this is no longer a surprise, because even for n equal to 1, that means we had only one unknown, we were able to reproduce the exact solution for the homogeneous part. So for n equal to 2, which is a better approximation, this does not come as a surprise. And like I said, the exact solution is linear, and it is only fair that a linear approximation should show it exactly. All right, let us go to the next case, where we will now say fx is a constant p. I will just give the values to you, that in this case f vector, which is f1 and f2, you can check it, work it out yourself. This should turn out to be p by 4 plus h, and this is p by 2 plus 2g. We already know what is k, so we can calculate d as k inverse f. K inverse I already gave you, this is 1/2, and f is p by 4 plus h, p by 2 plus 2g, and this value would turn out to be p by 2 plus g plus h, and this one would be 3p by 8 plus g plus h by 2. Once we know these values of d1 and d2, so let me remind you, these are the values of d1 and d2, and now we can estimate what is UH, which is the solution, and that's simply given as d1 n1 plus d2 n2 plus d3 n3. In fact, I can also estimate the derivatives. So if I want to calculate UH, x, then you will notice it is simply d1, because these are constants, so I use the chain rule, n1, x plus d2 n2, x plus d3 n3, x. So you can find out the first derivative also. Notice that the second derivative is 0, because all these functions, they only have, at least within the element, a constant first derivative. So if I ignore the element boundaries, that means x equal to half and so on, then the second derivative is identically 0. Of course, at the boundaries it is not defined, the element boundaries. Let us plot them. and educate ourselves as to what are the conclusions. So, UH x is given as G plus. So, if you rearrange all this, you should be able to see that it is H times 1 minus x, which is the homogeneous solution, plus a particular solution which is a function of x, and this is given as UH particular of x is given as p by 2 times n1 plus 3p by 8 n2. All right, let us plot it. So, again I draw the x axis. This is a half, this is a 1, this is 0, and this is u. So, if you look at the exact solution, that now looks quadratic. So, it would look something like this. Okay. So, there is a part here at x equal to half, which is 3p by 8, and this part at x equal to 0 is given as p by 2. So, what I have drawn here is the u exact particular. Now, if you plot the numerical solution, the discretized solution from the finite elements, magically you are able to recover the exact values at the nodes, and of course in between it would be linear. So, this curve is piecewise linear, which is UH particular. So, again we conclude from this that the solution is exact at x equal to 0, half and 1. I now move on to plotting the slope. So, this is your x axis, this is the slope, and let us make these so this is a quarter, a half, 3/4 and 1. And what you would find is that the exact solution has a linear slope. So, this is a value of minus p, this is minus 3p by 4, this value is minus p by 2, and this value is minus p by 4. So, this is the exact slope. So, u exact particular comma x. Because we are using two elements, so in each element the slope is constant, and it should not come to you as a surprise. This is what the slope is from the finite element method. So, this over here is u h particular comma x. So, I will just write here that the derivative is exact at x equal to 1/4 and 3/4. So, when we took one element, the slope was exact at one point, when we took two elements, so this is element 1, this is element 2, again the slope is exact in each element at one point. Okay. Of course, by the very discretization, the slope is constant within an element, so it can at the most match this linearly varying slope at only one point. Okay. All right, let us look at now a more complicated case which we have done earlier for one element, and that is the case 3, but this time with fx equal to a linear qx, where q is a constant. Let me give the values of f for you. So, with this q being constant and f being a linear function, you can evaluate f to be q by 24 plus h, and f2 is q by 4 plus 2g. And one can again calculate what is d, which is k inverse f, and this would turn out to be, I am just giving you the values, you can check them, work them out, q by 6 plus g plus h, and this is 7q by 48 plus g plus h by 2. So, I can now write down what is my UH particular. So, I would have to again write down UH as d1 n1 plus d2 n2 plus g times n3, and then take away the homogeneous part. So, the part that remains, the particular solution, is q by 6 times n1 plus 7 q by 48 n2. Let us plot them, okay, just like we did for these cases. So, here is a plot for u, and then I am going to make another plot for u particular comma x. So, this is the x axis. All right, the first, this is 0, this is 1, and that is a half. So, if I look at the exact solution, this time it is cubic. Okay. So, the exact solution would look something like this. So, this is u exact particular, it is cubic. If I try to superimpose on this the numerical solution, that would be piecewise linear, and what we would find is that this value turns out to be q by 6, and this value turns out to be 7q by 48, this value over here. So, the numerical solution is piecewise linear. This is u h particular. Again, I could conclude that the solution is exact at the boundaries and at midpoint, which is also a node. Now, I move on to the slope. So, this is 0, this is 1. The solution, the exact solution is cubic. So, the slope is going to be quadratic, and it looks pretty much like this. So, this graph that I have shown you is u exact particular comma x, and let me mark some values. So, this value turns out to be minus q by 2 and at x equal to half, this value turns out to be, I do not have that value, but I can share with you what are the values that you get from the finite element analysis. So, that is minus q by 24. So, this is the value that I would generate from u h particular comma x, constant in each element, and this value is minus 7q by 24. So, derivatives are exact at 2 points. All right, so let us summarize from what we have done so far. So, let me just make a summary. So, we have illustrated how the finite element works. Okay, we showed you example of one single element and then two elements, and the conclusion is that the homogeneous solution, that means when f is 0, so UH is exact when f is 0 in all cases. So, whether you take n equal to 1, n equal to 2, you are able to reproduce the exact solution. The second observation is that the Galerkin solution with the linear finite element approximation is exact at all the nodes. So, these nodes are the points at which these shape functions have discontinuities, and irrespective of how complex f is, I am always able to retrieve the exact solution. That is already quite an accomplishment. Okay? So, even when the solution, the exact solution is not linear, it could be quadratic or cubic, at least at the nodes I am guaranteed an exact solution from the Galerkin method. This is already a very important property, but I hope this does not get you carried away. This property is not going to hold for all equations. Okay? This is a very special case, an elliptic equation in 1D. If you do the same analysis for Navier-Stokes, then you are not guaranteed nodally exact solutions. It is not just the solution which is important, the derivatives are also important. For example, in heat transfer, u could represent a temperature and u comma x would represent flux. Similarly, if you look at solid mechanics, you have displacements and then strains. In fluid mechanics, you would have velocities, and the derivatives would imply they are related to stresses, strain rates, and therefore stresses. So, they are also of engineering interest. And what we find is that in each case, irrespective of n and f, the slope or the derivative is exact at one point in each interval or subinterval or element. So, with this example, I hope you are able to understand how the finite element method works. and we will continue this discussion in the next session, where we will generalize the finite element space and talk about a general implementation of the method. Thank you very much.